Test, test.
So we're just going to let the start when it's not the first time? Yep. Okay.
No introductions.
Okay. Yeah, apparently that's what we're going towards.
Okay. Right, I'll let people slowly trickle in. Can you guys hear me okay? Is the mic? I have to,
It's on.
it is on. Maybe put it a little higher. It's still working for the room. Okay. Okay. So welcome to day 2 of the dark matter lecture. So yesterday we ended more or less here, which was kind of putting a map of the options that we have for dark matter. So we went through these various arguments, first talking about the evidence for dark matter and how this gravitational evidence starts to give us some clue for what the identity of dark matter can be. And so we looked at a few of the observations and then could pull out some of the properties of dark matter. And through that, we saw that a priori there's a very large range of masses that the dark matter can live in, almost 90 orders of magnitude in mass. But then if we started to look at things a little more carefully, we could make some more precise statements. So for example, if we had a bosonic dark matter, there was a lower limit. So all of these, of course, are kind of tilde level. But there was a lower limit of about 10 to the minus 22 eV. If we had a fermionic dark matter, there was a lower limit of about 70 eV or 100 eV. This is known as the Tremaine gun bound. If we had something that was in thermal equilibrium with the plasma in the early universe, this set a bound of kV-ish. And then if we needed things to be a point particle rather than some composite object or macroscopic object, we have this Planck scale that's set up. But of course, we can then also have macroscopic things be the dark matter, so solar mass and above objects. So that seems like quite a lot of options. So how do we go about studying dark matter when we have such a large range of parameter space to study? So the fact that we observe dark matter, we have a sense for kind of what masses it can be. Another question we should ask is, how do we make dark matter? How did the dark matter get there? And what I'm hoping to do today is to show how the ways to produce dark matter also give us some guidance for how to prioritize within this mass range. It's not a free-for-all necessarily, right? Because we have finite resources in the world. So to start off with, I wanted to talk about how much dark matter there is. So the question is, so how much dark matter is there? And this is a number that we can get from the CMB, right? So the CMB tells us, particularly if I look at the Planck 2018 results, it tells us that we have some critical density of dark matter, which is given by the omega times little h, was related to the Hubble constant, which is about 0.12 plus or minus 0.001. Okay. What is little h? So this, of course, comes with an asterisk. If you guys have been following the H naught tension. This is defined as small h times 100 kilometers per second per megaparsec. And here's the asterisk part. It's a roughly 0.68 times 100 kilometers per second per megaparsec. Okay, so this is the rate of expansion today. Okay, so our goal is to figure out how do we get this, what we call observed relic abundance of dark matter. So the average dark matter density today, so I'm just going to put some numbers down here. So we also have the average dark matter density. Is given by what's known as rho critical. There's a little bit here. Which is defined as omega c, rho sub c, which is omega c times rho crit, which is omega c times 3 h squared over 8 pi gn. And so from this, we can put in some numbers, and you get that. Today, this is about 1.26 times 10 to the minus 6 GeV per centimeter cubed. And to convert into natural units, times 10 to the minus 11 EV to the fourth. Okay. So what we want to figure out is how do we kind of populate this this dark matter here. Okay, so how do we start? Well, for much of the early history, the constituents in the early universe were in thermal equilibrium, like the photons and like the plasma. So we have this, what we call a thermal bath. And departures from this thermal equilibrium in the early universe lead to a lot of interesting effects, kind of leads to us being here. So you need it for baryogenesis to get some net baryon number. You need it to produce the light elements. And you can also, through this departure of thermal equilibrium, get dark matter. So suppose we have this dark matter that's produced via this thermal bath. So let's suppose it's produced from this thermal bath. This I'll call thermally produced dark matter. Sometimes you'll hear this category of dark matter called thermal dark matter. There's a little bit of ambiguity of what that means, whether or not it's in thermal equilibrium or just thermally produced. So you'll see that what I'm calling thermal dark matter can not be in thermal equilibrium with the plasma. So let's see. So this is what I'm going to call thermally produced. So how do I determine kind of the abundance of the dark matter in this situation? Well, this abundance is governed by a Boltzmann equation. So this is right bucket. Right, so what does the Boltzmann equation do? It kind of tells us the behavior of a collection of particles. And if we were in full equilibrium, this is what the equation would look like. So in full equilibrium, we have that the rate of change of the number density times the volume, so this is the scale factor here, cubed, is 0. Right, so in equilibrium, the co-moving number density doesn't change. And so if I go and work this out, right, so a nice product rule from calculus, you get n dot plus 3 h of t, n of t equals to 0, where here it's the same Hubble as before. And if you go and work this out, you see that this is obtained from getting a dot over a. So how do we leave equilibrium, right? So how do we start to change things? Any ideas? If you're expanding too fast, what would that? What do you mean by?
Like if the particles can't interact with each other.
Yeah, so we're getting yeah, you're on the right track. So we have, when you say the particles can't interact with each other, we're assuming that there's some kind of interactions between the particles. So in particular, if we want to leave equilibrium, you can get this from, for example, number changing processes. Okay. So we can get departure from equilibrium. If there are number changing processes. So in particular, I have n dot plus 3hn. What are some options for number changing processes? Annihilation. Okay. So if I have annihilation, I'm going to put a minus sign here. Looks something like this, where I have n squared minus n equilibrium squared. Right. So this is from annihilation. Any other possibilities? Cannibalism. I'm going to skip cannibalism because it's a more specific. You can kind of fold it in to here. Decay. Yeah, decay. So, yeah. So in this lecture today, I'll kind of do the classic freeze-out story, and of course, then at the end, I'll talk about all the different exceptions that one can get around, including cannibalization. If you guys have heard of this. Sounds intriguing. Yeah. Yeah, so another option is that we can have the particle decay. Okay, so this is from decay. Okay, so we have this equation. This is the kind of the vanilla Boltzmann equation for determining the abundance of dark matter that is thermally produced. So we have on the left-hand side kind of how this number density changes, this co-moving number density changes. If there's no departure from equilibrium, and so for example, no number changing processes, this equals to 0. So we get this first line here. But if there are number changing processes, then this quantity on the left-hand side will be affected by either annihilation or the decay. The other thing to note here is that annihilation has n squared. Why? Because it has 2 dark matter in the initial state, whereas the decay only has an n. So this equation can be instructive to look at in some limits. So if we look at the limits of it, so if either gamma or sigma v are large, compared to h, what do we see? So if these quantities are large, if you go and work this out, you'll see that the number density n is driven towards the equilibrium value. So n is driven to n equilibrium. If I write here, can people see? I have one more line to write.
You can always move it.
Yeah, I'll do this. But what's the other limit? The other limit is if h is large, so h is much larger than the interactions. Any thoughts for what happens to the number density? So you can think about what do we mean by that? It's saying that sigma v and gamma are small. So if you take them to the really small limit, we kind of go back to something. Yeah, we kind of go back to this situation where the n is quote unquote frozen. It's a fixed value and it just expands with the expansion of the universe. So let's look at a specific example. So here's an example. So I have a situation where I have some chi1, chi2 going into chi3, chi4. So this is the interaction that I can put in for my chi's. Then, and now I'm interested in what is the change in the number density for particle 1. Okay, so particle 1, particle 2, particle 3, particle 4. So the change in the number density for particle 1 I'm going to call that n1, is given by a to the minus 3 d n a cubed over dt. And this is given by sigma v, n1 naught, n2 naught. So here I'm changing notation a little bit. The naughts are equilibrium values times n3, n4 over 3 naught, n4 naught, minus n1, n2, n1 naught, n2 naught. Okay. Where here this sigma v is given by, it's basically sigma v of chi1, chi2 to chi3, chi4. Okay. And then this means in thermal equilibrium. Okay. So this is the most general scenario for here. But let's make some kind of simplifying assumptions. Let's consider a scenario. So let's consider a scenario where n3 and n4, so the final state particles, are in equilibrium. So n3, n4 equals to n3 naught, n4 naught. And that I only have one species in the beginning. So particle 1 and particle 2 are the same thing. So n1 equals n2, and then we call this n chi. So if I go and put these back in, and this tells me that I have d n chi a cubed dt equals sigma v n chi naught squared minus n chi squared. So pictorially, what I'm saying is I have some interaction here. I have a chi, let's call these y. And these guys are in thermal equilibrium. Okay, so we have this. This is our Boltzmann equation that we want to solve. But it can be useful to introduce some new notation. And in particular, let me introduce a quantity I'm going to call y. Actually, so I shouldn't have called these y. I'll call these z. Some y of chi, which is defined to be the number density over the entropy. The reason why I want to do this is then I can use the fact that entropy, the co-moving entropy, is conserved. So use the conservation of co-moving entropy. So specifically, what does that mean? It means that the entropy times a cubed is a constant. To get, so if I plug in this into here, I can rewrite this as n dot plus 3hn equals s y dot. So the left hand side. So then using this, I can rewrite things. And let me define something else. I'll define it in a second. You can look at the change in this this yield equals minus x s depends on n chi h n chi v y squared minus y naught squared. where here I've introduced another variable, x, which is defined to be the mass of the, the dark matter over the temperature. Okay. Okay, so what have we learned? So after writing, kind of doing this manipulation and writing the Boltzmann equation in this form, we can make a few observations. So what have we learned? Well, one, we have an expression for the evolution of y, the yield, as the universe cools. So have an expression. Okay. So that's just the, I guess we haven't learned that. We just wrote it down. What is this y? It's the rescaled dark matter number density. Rescaled to entropy. And in fact, it kind of removes the effect of the universe's expansion. So what I mean by that is if we look at the expression with the n, there's this 3hn term, whereas in the expression with the y, we don't have this term with an h times the n. Yeah. So there's been several steps. So dot is time. X is related to temperature. So you have to do the chain rule a few times. And then, yeah, those conversions also depend on the cosmology. So yeah, I skipped through a few things here. But yeah, good question. So y is the rescaled dark matter number density. And by writing things in terms of y, we've removed the effect of the universe's expansion. So remove what do we also see? So any change that I get in y comes from interactions of the dark matter with states that are in equilibrium with the photon bath. Photon bath. Just a reminder, these are things that we've learned. What else? These changes are encoded in this sigma v. So it's governed. And what is the sigma v? So it's the velocity averaged section. So the angle brackets tell me it's the velocity averaged. And so why did we want to calculate the yield, right? What was our goal? Our ultimate goal was to figure out how to get this omega c. So once I have the yield, I can then calculate omega c in the following way. So it's the fraction of the critical density due to dark matter is then given by omega chi equals m chi s naught, so that's s today, y today, divided by rho c. Okay. So the goal here was to get some expression to calculate the yield. Why did we want the yield? Because then we can plug it into this equation, and then we can calculate what omega is. And we set this omega h squared equal to 0.12, and we can make some statements about the interactions here. Okay, so this is kind of a general statement. So I wanted to go through then a few instructive examples.
There's a question
Yeah.
here. Great. Why not and why not there? One is the equilibrium, the other one is today, or they're the same?
Yes, let me. Today. Good, yeah. That's what happens when you write your notes in different periods. Yeah.
When you have S of m chi and h of m chi, should I think of S and h as functions of temperature?
Yes.
Or plugging in mass as that temperature?
Yeah, so it would be the temperatures out of the mass of the dark matter. Yeah, good. That's a good question. Yes, I skipped over that. So here I have S as a function of m chi. I could have written S as a function of T as well. But I'm interested in the T at m chi, the temperature equal to m chi. And H is also a function of temperature, so I want the value of H when the temperature is equal to the mass of the dark matter. Okay. Okay, so again, so this was to kind of figure out how much dark matter is there. So for the rest of today, we're going to talk about how do we make it. And again, like I said at the beginning of the lecture, by studying dark matter that can have a viable cosmological history, I would say these are the models that perhaps are the most compelling, because we have a story for how it came to be. And then once you can understand how we make the dark matter, this kind of fixes the properties of the dark matter, and then you can kind of focus on looking for these theories, right? So kind of historically, this has been sort of a guiding principle for how we've prioritized the searches for dark matter, right? So we have these 90 orders of magnitude, but most of the effort in the last few decades has been focused in a few key spots. So what I hope to show you today is why those were the areas of focus. Okay? So basically, let's say the most compelling theories come with have a viable cosmological histories. Viable. This is not to say that we should only study these theories, right? Because we can spend a lot of time studying these theories with these viable cosmological histories, and we don't find anything. So I would say it's still worthwhile for maybe some people to look at things that maybe we haven't quite figured out the cosmology, but this is also something that one can study, is given some model, can we come up with a viable cosmological history for it? Okay, so how do we make dark matter? So we can categorize this question in a few ways. So one question you can ask to help us get started is, was this dark matter ever in thermal equilibrium with the Standard Model? I remember yesterday we ended up with that chart, and if we have a dark matter that's in thermal equilibrium with the Standard Model, we were forced to live above a keV in mass. Right? So now I'm looking at this subset of that diagram. So the first scenario we'll study is yes, it was. And let me call this a thermal relic. So this is kind of related to the example that I just worked out over there. So in this case, what do we have? So we have the dark matter interacting with the Standard Model. So it interacts through reactions that keep it in thermal equilibrium. So what happens here? Well, what's going on? So we have these reactions. The dark matter and the Standard Model are reacting with each other, going back and forth because they're in thermal equilibrium. But in the meanwhile, as you all have pointed out, the universe is expanding. The universe is cooling. So the number density of these particles is gonna decrease. So as the universe cools, the number density of particles so let me just, right here, what do we have here? We have some dark matter going back and forth with the Standard Model. Okay. So as the universe cools, we start to dilute all the stuff that we have in the universe. And then what happens? Right, so what are the processes that are going on? We have these reactions that are happening, and simultaneously we have the expansion of the universe. So we can compare these two things, and what you'll see, or if you think about it some more, is that at some point the universe has expanded. The rate of the reactions no longer keeps up with the rate of expansion of the universe, okay? And so it kind of cuts off these interactions. Okay? So at some point, rate of the reactions, let me call it gamma, is smaller than h, the expansion rate of the universe. So what happens in this case? So basically it's saying I've shut off this process. So say gamma is this process. So if I've shut that off, what have I done to the dark matter? So what were these processes doing for the dark matter? Yeah, so these were the processes that kept the dark matter in thermal equilibrium with the Standard Model. And so when I'm at this point, when the rate of these reactions can't keep up with the expansion of the universe, I shut these off, and the dark matter is no longer in thermal equilibrium. So what happens here is the particle goes through what we call thermal decoupling. And it's no longer in thermal equilibrium. And this is what we know, actually, you guys have probably heard this term. What do we call this process? Freeze out. So this is known as freeze out. All right, so here's kind of the big picture idea of how thermal freeze out works. So let's look at, let's see, how do I want to ask this as a question without giving away the answer. What were the properties that we needed for a dark matter candidate? We needed it to be matter. We needed it to be dark, meaning that it interacts almost minimally with the Standard Model beyond gravity. And we need it to be stable. So given those properties, are there any particles within the Standard Model that satisfy those conditions? Maybe. You guys think of, let's say, a particle that doesn't experience electromagnetic interactions, so it's some neutral thing, and it doesn't experience the strong interactions. Neutrinos, yeah. So in fact, we have a dark matter candidate within the standard model. So let's look at what goes on with the standard model with neutrinos. Why are we not done? Why am I still giving these lectures? Yeah, question. The interaction rate, does it depend on temperature? I think it depends on exactly what process you're looking at. Yeah, so yeah, of course, yeah, the interaction rate depends on temperature.
Isn't the neutrino mass below our fermion limit from last time?
Yeah, so we'll see. There's a few problems with the neutrino, but it's always good to say, but we have something. I went a little bit backwards in some sense, which is that we knew we needed these properties of dark matter. So then I could have just started with, okay, what about the neutrino, the standard model neutrino, before, and then going through all the different evidences and seeing that it didn't work. So here's going to be another, spoiler alert. There's another reason why the neutrino can't be all the dark matter. Yeah, so we'll see specifically what goes wrong. Okay, so let's start with the standard model neutrinos. So as we say, they satisfy a lot of the properties that we wanted, right? They're dark-ish. They're stable, or at least very long-lived, and they have the characteristics, essential characteristics for a dark matter candidate. The rate that I'm going to look at here is going to be, so we have electrons and positrons in our plasma going back and forth into nu bar. This is something that happens in the standard model. So we have something that looks like this. Right, so we have E plus, E minus, going to nu bar. This is a question from the previous lecture. I don't remember if you got to it. What goes in the squiggle? Yeah, the Z boson. So I'm gonna, instead of looking at this, I'm gonna say that we're in a regime where I can consider the 4 Fermi interaction, and we'll see towards the end why this is a valid approximation to make, which is that I have my E plus, E minus, nu bar, and here I put in G Fermi. Okay. So from dimensional analysis, so what is this rate? Well, what do I have? I have this coupling, G Fermi. And what do I need? What do I need the dimensions of this guy to be? In terms of, like, say, MeV. What's the cross section? Cross section, centimeters squared. How do I write centimeter? How does centimeters and, let's say, GeV relate? Yeah, so this needs to be like GeV to the minus 2 or some energy to the minus 2. What are the dimensions of G Fermi? The same units, yeah. So are we done? So Hangame was just asking, does the rate depend on the temperature? So it does. So I want to put in a temperature. So these I want to figure out what are the exponents going on here. So if this goes like G Fermi, what is the cross section? It's going to be this thing squared. So this then gives me 1 over energy to the 4th. I want to get 1 over energy squared. So that tells me this goes like temperature squared. Okay. So of course there's all these prefactors that sit out in front, but this will get us most of the way there. So then the rate, this gamma, is given by the number density of the particles times sigma v. So what was the process that we were interested in? It's this, which number point is it? The third bullet point I want to look at. So in the third bullet point, what I'm saying is that I want, so we want to compare this rate at some temperature I'm going to call T nu, which is going to be the neutrino freeze-out temperature, H at that same temperature to determine neutrino freeze out. So for a relativistic particle, you guys remember maybe from Kolben-Turner how the number density scales with temperature. So N relativistic. I don't expect you to have it necessarily memorized. So this goes like temperature cubed for a relativistic particle. Again, what do we mean by relativistic is when the mass is a lot less than the temperature. Sorry, my writing is getting smaller and smaller. What about Hubble? In fact, let me look at Hubble squared. This is defined as 8 pi gn rho over 3. So if I take a radiation-dominated universe, like I'm assuming this is all happening during radiation domination, Hubble goes like 1.66 times g star of t square root t squared over m Planck. Okay, or this quantity here is the effective number of relativistic degrees of freedom. Okay. Great. So now we have, so I covered it up. So this is going to go like n gf squared t squared. Okay. So we want to compare this gamma to this Hubble at a specific temperature. We have expressions for both of them in terms of the temperature. So let me just plug these in. And in fact, I'm just going to say this is like t squared over m Planck. What we then get is that we have G Fermi squared T nu to the 5th. Which goes like T to the 5th G Fermi squared. So here, what have I done here? I've just plugged in this relationship. So we have G Fermi squared T nu to the 5th, which I got from this. And this equals T nu squared over m Planck. Okay. So I can then pull out what T nu is. And this is about G Fermi times m Planck squared to the minus 1/3. If you go and plug in these numbers, right, these are just constants that we have. This is about 1 MeV. And what we know about neutrinos is that they're very light. They're much less than an MeV. And so we see that neutrinos are relativistic. Or they freeze out while they're relativistic. So this tells us you freeze out so aka they are hot. Okay. The other thing to note is what is this temperature? It's an MeV. What were the interactions that I was looking at? It was through the weak bosons. What are the masses of the weak bosons, roughly? Yeah, a little under 100 GeV, 80 and 90 GeV. That's much bigger than this temperature. So writing this effective theory is okay. We're at energies much, much below the scale of what's going on in the blob. Okay, so we've calculated at what temperature the neutrinos freeze out. We saw that they were hot. So let's now calculate what is the relic density of neutrinos today. So I'll go back over here. What time am I supposed to end at?
At 12.
At 12, okay. You guys are right. It goes slower than I thought I would.
It's not just you.
It's not just. Okay. Yeah. Questions? Would raising it up. Oh. So this last one is gf squared, t nu to the fifth equals t nu squared over m Planck. This is just setting gamma and h together. This gives me that t nu is gf squared times m Planck raised to the minus 1/3, just from doing the calculus here, which is 1 MeV about, which is a lot larger than the neutrino mass, which tells us that neutrinos freeze out while they're hot, or while they're relativistic, so they're hot. A hot particle. Okay. So next thing to calculate is, what is the relic density so how many neutrinos are there now? So what is the relic density of neutrinos? Is this font okay? So again, we have our yield, which is n over s, the number density and entropy density. And we have that y goes like n a cubed because of the conservation of entropy, where sa cubed is constant. So we have this relationship here. So if we don't have any entropy that's injected between the time that the neutrinos freeze out and today, we can write that the yield at freeze out is equal to the yield today. What was the yield at freeze out? It was the yield at t nu. And then we only need to worry about the fact that the only thing that's changing is the universe is expanding. So what is y freeze out? Is n at t nu over s at t nu, which equals rho t nu divided by m nu s of t nu. Here s, I'll just write what it is 2 pi squared over 45. So I won't go through where these come from. This is the times t cubed. And the number density is given by 3 zeta, Riemann zeta function. This is a zeta, which I'm not very good at writing. Zeta of 3 over 4 pi squared times g times t cubed. So this is for a relativistic species. If you go, again, this is like a chapter in Kolben-Turner. You can go and work out the integral. You get an expression that looks like this.
Are those the same g?
These are different g's. So in this case, this g is going to be equal to 2 for a single species, because we have the two spins. And this g star of s at t nu, right, counts what are the relativistic species that we have around here? We have electrons and photons. And you should get 11 halves when you're at an MeV. Okay. So with these expressions, I can then plug in what y freeze out is. This is 135 zeta of 3 times g over 8 pi to the 4th g star of s. Plug in these various numbers. I'm going to skip a few steps, so some magic happens here. And I can get that the relic abundance of neutrinos, so omega, is about 0.12 times g over g star s, the sum of the neutrino mass over 4.1 eV. Okay. So I'm writing it in this way because we're interested, the neutrinos can be all of the dark matter. So I'm setting this equal to 0.12, and then parametrically putting the other variables that enter. So we have a limit on the sum of the neutrino masses from CMB. So the current bound tells me that m nu has to be less than about 0.1 eV. So if I go and put that in to this expression here and put in these values of g and g star, we get that omega nu h squared is less than or equal to 0.2% for a single massive neutrino species today. Okay, so we saw two issues with the neutrinos. One, before we even started, you guys pointed out, was that the neutrino masses that we know, this bound, is already below this thermal bound. So that should have already clued us in. But then we kept going, and we wanted to calculate, okay, how many neutrinos can there be now? So if you go through and go through the argument with this mass bound on the neutrinos, we saw that it could only be a fraction of a percent of the relic density, which is not 12% dark matter. Okay. So it was a nice idea. One should always start with, what do you have? Let's be economical. We have neutrinos. They satisfy a lot of the properties of dark matter. But it turns out they don't satisfy all of the properties we need the dark matter to have. Okay, so this was, what were neutrinos? We saw that they were relativistic, right? So the next thing we can think about is, what if we had a relativistic species? So I made some statement earlier that dark matter needed to be cold. What goes wrong when it's relativistic? So that's going to be my next step. Yeah, question.
This current bound is for the sum of the.
Yeah, so I'm assuming if there's only one species that's massive and then the rest are massless, this is the maximum relic density it can be.
Also, what processes can change the entropy and break things?
You could have some process that dumps more energy, like some decay in the early universe that dumps extra degrees of freedom into.
Can I somehow manage that in order to increase?
Yeah, sorry, the question is, so we're trying to save neutrinos as the dark matter. And the question is, can we increase this bound? One of the assumptions that I made was that there was no change in the entropy, no increase in entropy between the time of freeze out and now. So the question, could I engineer some situation where I dumped in more entropy to get the neutrinos to be dark matter? I would say one could try. You would probably run into a lot of other issues. Like you probably screw up the CMB quite bad. CMB is pretty constraining. It's a very powerful tool. But good, you're thinking like a model builder of how do I get around these things? Okay, so that was neutrinos. Okay, that didn't work. Now let's see what happens if I look at a relativistic species. Okay, so now let's consider, so this is another example. Consider some chi, which was relativistic at the time of decoupling. So similar to the neutrinos, but not the neutrino. particular, let me consider the situation where this particle freezes out before the neutrinos froze out. So T freeze out is greater than T nu, which was 1 MeV. And let me assume that the neutrinos decouple instantaneously, meaning exactly when I hit 1 MeV, neutrinos stop. That's not actually what happens. It's a slightly more drawn out process than that. But for now, let's assume that this is instantaneous. Instantaneous. Then, at MeV, the number density of chi is given by 135. I also wrote it over there. Zeta of 3 times g over 8 pi to the 4th star s t freeze out s at t equals MeV. So that's slightly before this. And in this case, this value is 43 over 4 times 2 pi squared 45 t cubed. Okay, so once I have the n chi, I can calculate what y chi is, which is n chi at t equals 1 MeV, and s of the photon bath, t equals an MeV, which is 135. So I'm just copying over these expressions from above. G divided by to the 4th. That's 43 over 22. Okay. And once I have the yield, I can calculate what omega is. So omega chi h squared is about 0.12 times g over g star s m chi over n EV. So we see that we can get roughly the right relic abundance if m chi is between 1 to 10 EV. So assuming the following, that g is about 2, and that g star s at this freeze out time is some order 10 number, that m chi between 1 to 10 EV can populate the dark matter abundance. Okay, so what goes wrong here? If you have already pointed out when we were talking about the neutrinos, what already was wrong. So we're starting off with this assumption that we have some particle that's in thermal equilibrium with, so the mass we're saying is between 1 to 10 EV, but we know that if it's a thermal guy, it has to be above a keV. Okay. So but m chi has to be above a keV for thermal dark matter. So how can we salvage this? There's other things that other knobs I can turn here. So let me plug in a keV for the mass. I can try to manipulate how many the G star here. But if I still want to get this to be 0.12, then G star has to be over 1,000, which is a lot more than what we have in the standard model. So effectively, if I want a relativistic thermal dark matter, I would need to have some really non-standard cosmology. I would need to add a ton of stuff to get G star to be 2 orders of magnitude more than it is in the standard model. Okay. So include here, can get this if G star of S is about or greater than or equal to 1,000. This is much more than the standard model. So the conclusion is that freeze out of relativistic species only works in really non-standard cosmologies. So we start to see we have these constraints, right? We have these regions where we say if it's some thermal fermion, it has to be in this regime. But there are a lot of knobs to turn. So this is an exercise that some people enjoy doing, is saying, how do I get around all these things? So we saw here that you could, in principle, have some relativistic species be the dark matter if you put in some wacky cosmology. But then if you do that, then you have to make sure your cosmology doesn't, like, we can still get the universe that we live in now. But we're an empirical field, so we still have to satisfy data.
Just a quick question. Where did that thermal bound KV come from?
Yeah, so the question was, where did this KeV thermal bound came from? This came from the matter power spectrum of if you had something that was hot, it would suppress structure this was from the Lyman alpha, some Lyman alpha measurement. Okay, so let's see. I have 15 minutes to do the WIMP miracle. Okay, so we just saw that neutrinos don't work for dark matter because there's not enough of them to make up the relative abundance, and they're too hot. We saw that a relativistic species, like a priori, doesn't work very well unless you do something kind of drastic to the cosmology. So now let's look at some non-relativistic species. We'll start here. Okay, so what about non-relativistic? So what changes for a non-relativistic guy? So one change is that the number density, so we saw that the number density for relativistic species, which I think either just erased or is under here, went like t cubed. For a non-relativistic species, this value goes like g m chi t over 2 pi to the 3/2 times this exponentially suppressed factor of minus m chi over t. Yeah, question? A little larger, yeah. So the n chi equilibrium is given by g So two differences. One is this temperature scaling is like t to the 3/2 instead of t cubed. And then we have this exponential suppression. And we'll see that this exponential suppression is really, really key here. Right, so this is the key difference between a relativistic species and a non-relativistic species, is just this expression for the number density. So this will be key. So again, we start with the same story that we did with the neutrinos. where we want to find the condition for freeze out. So we have some rate, which is given by some n chi equilibrium, sigma v. And we want this to equal to h. I can start plugging in things here. And I get that n chi equilibrium is still okay. Just realized I'm getting smaller again. N chi equilibrium equals this thing, g m chi t over 2 pi e to the minus m chi over t. And we want this to equal to h over sigma v. So h was 1.66 times g star, root g star. Have some freeze out temperature squared over m Planck. Right, this is the h part, times 1 over sigma v. Okay. So I've just put in the expression for the Hubble, put in the freeze out temperature here, and move this sigma over to the other side. Once I have this, I can calculate the abundance, which is the m chi over s. What is n chi over s? Again, this is equal to h over sigma v. This equals h over s sigma v, which goes about like g star over g star s, 1 over sigma v, 1 over t freeze out m Planck, which equals square root of g star over g star comma s xf, where again x is m chi over t freeze out, over sigma v times 1 over m Planck. So what kind of values do we need to get a small yield? We need this to be about a little bit, we need this to be smaller than 1. We can get that if sigma v is sufficiently large. Okay, so we see that our freeze out is possible. Sigma v is sufficiently large. And what happens if sigma v is large? Well, if sigma v is large, then the dark matter interactions last longer, right? Because we can go to larger Hubble and still have this equality. And if they can last longer, it means that this n equilibrium is going to be smaller. Okay. So we also see we have this exponential damping, which I said was going to be important. When does that really start to kick in? Well, it really starts to kick in when the temperature drops. When the temperature is about the mass of the dark matter. Okay. So since n pi equilibrium drops exponentially once we hit temperatures is about m chi, we can estimate when the freeze out happens. We can estimate that this freeze-out temperature has to happen at some temperature below the mass of the dark matter, but not too much more. And it turns out, if you go through the calculation more carefully, that XF, so it turns out XF, which is defined to be the mass over the freeze-out temperature, is about 10 or 20, works out pretty well. So if I go and plug that in and calculate what omega chi is, right, this is n chi over s, which is m chi y chi s over rho critical. And this goes like g star square root xf over sigma v 1 over m Planck s over rho c. So putting in values for s, rho c, and x, we can then figure out what is the sigma v we need to get omega chi h squared to equal 0.12. So for 0.12, we need sigma v to be about g star. Actually, won't plug in xf yet. It's 1.12. Minus 9 GeV squared to the minus 2. And I can convert this to units that are kind of useful for other searches. And so this is about equal to 2 times 10 to the minus 26 centimeters cubed per second. Okay. So what kind of models would give us this type of sigma v? So particularly, let me look at this process where I have some chi going into standard model stuff. We can call this G and this G. And let's suppose these interactions are weak scale with some weak scale mediator. Well, in this case, sigma v is going to go like, and this has some mass of m chi. These are weak scale interactions. So sigma v goes like alpha squared pi over m chi squared, where alpha is just squared over 4 pi. So I want this to equal this value. So if I set that here, take alpha to be the fine structure constant, I get that m chi is about 300 GeV, which is also of the weak scale. So this is kind of an interesting result. So this is sort of alluding a bit to what we call the WIMP miracle, is you put in weak scale interactions. If you have weak scale dark matter particles, you get the observed relic abundance without having to do too much extra stuff. Okay. So I'm going to stop here for today. I'm going to kind of continue talking about this tomorrow morning. And then we'll start to expand, start to generalize this argument and see what else can we say about dark matter. So maybe I should just put the punchline here. This is the WIMP miracle. So this is kind of what drove a lot of the efforts for dark matter to be looking in this 100 GeV mass range for a few decades now. Okay, but we're going to go beyond the WIMP here.
What did you say the alpha?
1 over 137.
Oh, okay.
Yeah, the electromagnetic. Yeah, so this. So keep this in mind for tomorrow.
Any more questions? Yeah.
So, is the wind miracle currently in tension with experimental bounds?
I would say yes, the simplest WIMP miracle, like this WIMP miracle is very much ruled out. This cross section of 10 to the minus 26 is 20 orders of magnitude ruled out at this point. There are, like I said, there's always knobs to turn. So the WIMP is not ruled out, which is why it's still worthwhile to look at. And as we heard yesterday morning, like one of the ways to really fully cover the WIMP parameter space is to go to like high energy colliders, like the mu1 collider. So this is why people are still interested in studying the WIMP. But I would say this is the fact that it's not, that a lot of the parameter space has been covered is part of the reason why I haven't been thinking as much about WIMPs in my research. But we'll get to that tomorrow about what other things can we do.
One more question,
And if you have other questions that you think of later, like there's this lectures channel on Slack that you can post stuff.